And here we are with the chapter 2. We're actually calling this chapter 2, day 2. But it is technically chapter 2, section 5 in the textbook that we go off of. Either way, our objectives today are to review properties of equality and use them to write algebraic proofs. So the idea is that we've been using reasons like addition and subtraction, and so now we're actually going to talk about their official names of equality, and then we're also going to identify other properties of equality and congruence that we can kind of throw in there to use as our bank for what to pick for our reason column. So again, all about developing your proofs reason column. All right, so a proof, we may not have defined it that first day when we were doing algebraic proofs, but a proof is an argument that uses logic, definitions, properties, and previously proven statements in order to show that a conclusion is true. All right, so the idea is that your argument does need to be pretty foolproof, which is why you have all of those different steps that you're putting in there. So you can't necessarily skip too much because otherwise people aren't going to follow the logic of your proof or that the steps of that statement. So an important part of writing a proof is giving justifications, which we call those reasons, to show that every step is valid. As we gain more of our resources, we are going to be able to skip certain steps in our reasons, but right now we just get to explain every step and make sure that we're, it's going to feel redundant, but it just means that we're thorough. So the first properties of equality that you've pretty much already done are the addition property of equality, the subtraction property of equality. So all of these are ones that we have actually used in the previous day 1 work. So basically all it's saying is that you can add, in this case, a c to both sides of an equation and it's still going to be equal. Or you could, in this case subtraction, you could subtract a c to both sides of the equation, still true. Multiplication, you can multiply both of them by a c and it's still true. Or in this last one here, you can divide both of them by a number. So we already know all of those definitions because you know what addition does to a formula or an equation when you're working. The next thing that is going to actually be new is going to be your reflexive property. So it isn't necessarily, it doesn't feel like it's going to be necessary for a reflexive property of equality because you're wondering why anyone would ever need to say that A is equal to A because, like, duh, right? But it turns out that we actually will, in certain statements, have to kind of list off what we know. And so if we need to list off all of the sides, but let's say that, or all of the angles, and let's say that 2 of the angles share a side, right, in an adjacent angle, we are going to have to say, well, this side, even though it's shared by both of them, is equal because it's the same. So either way, we'll get to when to use reflexive property, but the idea is that it will be necessary and it will become apparent when it will pop up. The next thing is the symmetric property. So here we are with symmetric property, and all that means is that you can flip the order. So this is kind of like when we used to say things like x equals 5, super, but then for some reason when you were solving, sometimes it ended up being 5 equals x, and some of you are saying, oh my gosh, I can't stand it when the x is on the right because it doesn't feel like it's the right answer. This is the property that allows you to actually rewrite it so that it's x equals versus 5 equals. The next one is going to be your transitive property. Transitive property will come up quite a bit, and it actually is usually interchangeable with the substitution property. But either way, the transitive property basically says if you have something that's equal to, in this case, b, and then something else that's equal to b, you can take out the b's and just say they're equal to each other. So this transitive property here kind of cuts out the middleman. All right. And then the last one is substitution. So the reason that transitive very much looks like substitution is that I could have just substituted this c in here because b was equal to c. So again, substitution just kind of replaces something that's in there with a previous statement. So if you are taking something completely out and replacing it with something else, that's going to be your substitution. All right. The next pieces that we have also already used is the distributive property. So again, we know that we can say that we can distribute or multiply something into other pieces. And so just remembering distribution property as one of our reasons. And then we also have the fact that you're combining like terms. And again, it is the act of adding or subtracting, and so you could just go back to the subtraction property of equality or the addition property of equality. But I do like to kind of reiterate or kind of be more specific when it comes to combining like terms, because that is what we're doing versus just adding a constant. All right, so we're going to do this first one here, and it's going to be very much like our previous examples, and that's because in previous lessons I haven't necessarily done the work to the front loading like we did this time in Chapter 1, Day 1, or Chapter 2, Day 1. So instead, I'm going to work through my statements. So every time you do a 2-column proof, you're going to have your statements and your reasons. Just because you probably can't take the time to make a bunch of boxes as you go through this, most of the time when we do a proof, we'll have kind of reasons and statements that are numbered so that you can see how they match. So my first statement is going to be that I have a 4m. If I subtract 8, it'll end up being negative 12. And remember that the reason that you can have is given. All right, then the next piece that I'm going to do is technically I'm going to add 8 to both sides. But remember that we're not going to just put our little work right here. We're actually going to, over on the side, end up writing that we are using the addition property of equality. So over here, instead of writing addition or add anymore, we're going to write addition property of equality. All right. And then the result of the addition that would happen here is that you'd have 4m, and that would equal negative 4. Then the next step that we'd end up doing is division. So I'm going to write the division property of equality. All right, and then if I divide both sides by a positive 4, my m is going to be negative 1. And so I've moved from how this can actually show us that m is negative 1, and I've given a reason for every single piece. All right. So the next piece here is a little bit different, because notice that we do see the word congruence instead of equality. Okay. And so really the only difference is that we are now talking about symbols or shapes versus numbers. Okay, and so in the previous one, numbers was what we were doing with equality. But with congruence, we're using our shapes or items or existing properties. So the reflexive property is still true when it comes to what it means. It just means that the same thing is equal to the same thing. Symmetric property is still meaning that you flip things. And then the transitive property is still meaning that you cut out the middle. All it is that there's just this extra symbol instead. So remember that equality would be your equal sign, but congruence is the equals with the little tilde on top. All right. The last bit here, other than this remember, so we'll try this remember first. So remember that numbers are equal and figures or shapes are congruent. So this was supposed to be the congruent symbol, but of course the computer did not understand what that meant. The only other thing that I want to add to our list, so if we go through our reasons of what we have add, subtract, transitive, symmetric, but other reasons that we've defined already was the addition. Oh, sorry, I forgot the first word. Angle addition. That idea that you can add pieces of angles together to make the entire angle, and then also segment addition. So we have defined these in chapter 1, but the idea is that when you go through your reasons, because now we're going to end up having shapes or visuals of what we're doing rather than just the algebra of what we've been doing, we're now going to want to add those two to this. So addition property of angles and then also of segments. So when we get to this last example that we have, I think it's the last one. Oh, nope, we have two. We're going to write a proof and a justification for each step in order to figure out what x is. It doesn't say in here necessarily, but we're going to solve for x. All right, so if we want to solve for x, it doesn't look like there's a whole lot of room, but I'm going to put it over here. All right, so I've got my statements and then my reasons. All right, so what's going to happen is that we have this diagram, and anything that we take from that diagram is going to be a given. All right, so for instance, I am seeing that NO, the segment, is 4x minus 4. And actually, I don't want to say segment with the line above it, because I am talking about the length of it. So NO, that's an interesting segment, is 4x minus 4. I'm also going to be able to say that NM is 2x, and also that MO is 3x minus 9. So what happens is, if this diagram didn't exist and you only saw this proof, you'd be able to say, okay, well, this is what I was given, okay, and now I can use those pieces to, for instance, add things together and solve for x. This is a very large given. We also have, let's see, nope, the next thing isn't given. So the next thing I'm going to do is actually talk about setting up this problem. So setting up this problem, I'm actually going to use segment addition. And remember that segment addition says that you can take segments, break them into pieces, and they will add to the whole thing. So, for example, NM, that segment, plus MO is actually equal to NO. So each of those lengths of the segments, the little parts, will add to be the larger one. I have run out of room, so I'm going to continue on to another page here. So this one is our segment example. So our third step in all of this, after I've said that everything is adding to be the whole, I can use substitution to get that algebraic statement that I'm going to be solving. Because if I know that NM, for instance, NM is actually 2x, I can go ahead and write 2x instead of nm. So I've taken nm and replaced it. Then I know that nm can add to mo, and mo is 3x minus 9. So I'm saying that I could add it to mo, which is 3x, I don't know if it was plus or minus 9. And then we know that that equals NO, which in our diagram we've said NO is 4x minus 4. All right, and so again, I've replaced NM, replaced MO, and then also substituted NO as well. So all of those letters, or that geometry, has now all been replaced by algebra. And now we actually get to do the algebra steps of all of this. And so, for instance, the first thing that I'm going to do is combine some like terms. So, as you can see, 2x and 3x are both on the same side of the equals, so I'll go ahead and put them together and make 5x, but then I still have minus 9 and equals 4x minus 4. Boop. Then the next piece is going to be subtracting over the x's to be with the other x's. So I'm going to do the subtraction property of equality. And you'll notice that I'm starting to abbreviate some of these pieces because there's a lot of writing involved, and so prop of ec is what I said instead of property of equality. And once you subtract, for instance, this 4x over here to be with this 5x, we end up with just an x anyway. And so x minus 9 is going to equal, no longer a 4x because I took it out, is going to equal negative 4. Then in our next step, we can add a 9 to both sides, and so again, addition property of equality is next. And so I'm adding 9 to both sides, and now I know that x is 5. So of course that is what we were trying to do in this problem. The directions were solve for x, so we were trying to do that. And so we started with our givens, what's given in this diagram. From that diagram I'm seeing segments, and so I'll use segment addition. From there we substituted in each of our pieces and then ended up doing that algebra to find x. Alright. In our next one here, we're seeing angles, and we're going to end up adding the angles in order to find out what x is. So again, we're going to solve for x. And so we're going to start out with some statements and some reasons, and then of course we're going to fill in the algebra. So let's see if we can fit this all on one page. Alright, so the first thing is going to be your givens, and so we're going to take the time to list out our pieces that are given so that we can substitute them in later. So we have the measure of angle ABD, that top one there, and that is 3x plus 5. The next angle is DBC, and so that is 6x minus 16. And then the last angle is the entire angle, which is ABC, and that's given as 8x. So all of those are given pieces. The next step that we're going to want to do is our angle addition. So remember that angle addition tells us that we can take that large angle, which is ABC, and it will equal the sum of the two smaller angles. So it'll equal, oops, gotta write an M, the measure of angle ABD plus the measure of angle DBC. So lots of letters here. Then in the next step we can go ahead and do our substitution. So now we can be setting it up for solving. So instead of the measure of ABC, I'll go ahead and do 8x. Instead of the measure of angle ABD, I'll end up doing 3x plus 5. And then instead of DBC, we can put 6x minus 16. Now we get to do the algebra to solve this, and so I'll probably start with combining like terms. So I'm going to have to move to another page. This is our angle example. So as I mentioned, we're going to combine like terms, and so that left side is going to still be 8x, but then the right side we're going to combine the 3x and the 6x to get 9x's. And you don't want to do two steps at once, so we're just going to say that's 9x and then plus 5 and minus 16 still. If you are starting to use the word and in your reasons, that is not what we want to do. We want to make sure that each step has its own line. So then the next piece is that I'm going to subtract or add the 5x and the 16. So I'll do the addition, and actually this isn't even addition property of equality, it's just addition. but if you wrote of equality, that's fine. And then minus 11 instead of 5 and negative 16. And then we're going to combine some like terms by subtracting this 9x. So subtraction property of equality tells us that we can have negative 1x equal to negative 11. And then that last step is pretty much always division. And so now we know that x is actually positive 11. All right. So again, hopefully that makes sense. The idea is starting with geometry and then flipping to the algebra so that we can actually figure out what the variable is. Potentially, they may have wanted you to then say what is the measure of ABC, and so you might have had to plug in an 11 and then realize that it's 88 degrees. Okay. But that might be the next step of what we're doing. All right, so those are your notes, and you will have an assignment that goes through this kind of problem.